Welcome to Udacity. Welcome to Udacity's Nano Degree program, and a warm welcome to Udacity Mentor Guidance session. I'm excited and really happy to be part of this session and welcome you all. And let's begin the session. First, let me walk through a brief introduction, and we will look at who am I and why am I here and what we're trying to do. And I got to mention we are always here to help and guide you with your nano degree program. And what makes it eligible for me to think that I can help and guide Udacity participants? Well, I completed the nano degree program and I've been through all the challenges and I've understood quite a lot and thoroughly enjoyed that learning experience, challenging one though. So I felt it's better to come back and help others as well. And that's the reason why I picked up the mentorship, and here we are. So little bit about the mentorship program. We are here to help and guide in every part along the way. So sit back, relax, and enjoy whatever we discuss. The notes will be provided and the details will be provided as well. Any codes, anything we discuss, it will be provided through GitHub as well. So you've got everything. There is only one thing we require from you, and sit back, enjoy, relax, and try to understand what's going on. And if you have any queries, we will help you out with that as well. So what is my background and where do I come from? Well, having a cup of tea, and you might have guessed it well. It's Shakespeare's county. It's Warwickshire in England, and that's where I work on various artificial intelligence based tool sets, and I have been doing it for almost last 20 years in the industry for automotive and aerospace. I come from a mechanical engineering background, so I have a master's in mechanical engineering, specializing in manufacturing execution systems, information management, robotics, and artificial intelligence. Almost 20 years into aerospace and automotive engineering across Europe and Asia Pacific, mostly in engineering research segments. Primarily, my experience was into artificial intelligence through deterministic methods, and modern artificial intelligence is more about probabilistic methods, and that transition happened through Udacity, through the nano degree program, and I enjoyed that transition as well. So that's primarily the motivation behind stepping to Udacity and trying to make the transition from traditional artificial intelligence to modern artificial intelligence. That should give us the brief overview of who I am, and well, you are in safe hands to be sure. So we will try and help you and guide you out with other things. Let's proceed. So the topics which we are going to cover today, let's look at the topics, and let's look at why and what's and how, and how we are going to go about it. It's going to be short presentation, so my objective is to give you with kind of a framework which will build you the mathematical intuition, which will build that neural network based intuition which you can take to the real world and apply it into the real world scenarios in the industry as well. Prepare you in better shape and form to suit yourself in the real world, and this presentation is primarily aimed towards doing that. And the topic which I picked up is from chapter 4 of artificial intelligence with the neural networks and Python. It's being taught by Luis on the chapter, and everything we do here will be adding on to that well built and beautifully presented program which covers almost every topic which is essentially anyone should know. Sometimes having a different perspective always helps. Having some real world examples, different kind of examples, which you haven't seen in any books, any presentations, or YouTube videos, or documents. And having that kind of an example, looking from a different perspective, always helps. It freshes the mind, and you go back, you look at it from a different perspective, and that's the objective behind the presentation, to help you with that foundation. And when it comes to mathematics, there are no shortcuts. We all know it. The hand calculations are the first step, and after that we go towards building some form of source code and replicating it, visualizing it in a graph. And primarily what I found while working across all the mathematics behind artificial intelligence in the industry is that once you have the real world scenario, once you have the requirement, anybody would be motivated to explore and enjoy that journey. And that's exactly what we're trying to do here. Create that real world scenario, that bridge which will help you to understand and challenge you to go and explore and discover the details. So let us get into the topics which we are going to look at today. It's going to be neural networks, a brief overview, and then my journey, what made the difference, and how did I go through it, is something which we got to look at. We will look at forward and backward pass, why it's important, and what's happening, and how to understand the internals. What exactly are the internals? We'll look at some unconventional examples, I should say, and the analogies. We will look at the mathematics intuitions behind it. That's something which Louis has been talking to us about, even Sebastian Thrun. So understanding the mathematical intuition forms the core, because that's exactly what's going to help us in the industry, in the real world, to solve problems. Some of you may have already known it if you're from industry, and it's better to mention it. So we are going to briefly look at that. We will look at two mathematical topics. I'm not going into the details by the blackboard and whiteboard and markers and long formulas and calculations, but I'm going to mention it briefly. If you require further details, just let us know. We'll look at the mathematics, we will look at the graphs, we will look at how to explain it in detail through a code, and everything will be through GitHub, and we will provide you with the right references. We will review all the topics at the end of the presentation, so you don't have to take the notes, and the notes will be provided to you as well. Yeah. So let's proceed further. So neural networks overview. What exactly is a neural network, and how a neural network simulates the working of a brain, almost similar to how a human learns by pattern matching, and how to take it to the real world and deploy it. Most of us have at least one or two encounters with neural network based gadgets. It's there in phones, it's there everywhere almost now. We might have seen it. So how exactly the process happens in the industry? Well, we know most of the things. Let me briefly run through it. First, we build a network, we train it, we test it, we optimize it, we validate it as well. And then there's one more step to that in the industry. We deploy it and maintain it as well. So sometimes the deployment may require you to switch from Python to C for performance. So that's something which I wanted to mention in the real world. So the training is the step where you provide a large data set, and then you find the difference between the way your model calculates it, the results, and the real world results which you know, and you feed the real world scenario through feature engineering by engineering the features and making sure that it fits the model, and the model fits whatever is required as an output for you through classification and regression. And once you're done with training, you test it, and then you validate it with some of the real world scenarios. This is where everything happens, and then you deploy it after thorough validation. So these are being on the one side. What exactly is required to understand neural networks? Training the neural networks helps you to understand the architecture, definitely, but what is happening internally, and why should you understand what's happening internally? Well, in the lesson there are references to Andrew Karpathy's why we should understand backpass, why should I understand the optimizer. Those are really good links, and it's nice to have a look at it. Now we are going to talk about why and what, and how exactly this works, and what should be our approach to it. And I will share with you my approach, my personal experience with it. Most of the examples which we see here may not have been there in any books or any videos or anywhere in the Google. So it's going to be a refreshing experience when you go back, you look at things in a fresh perspective, and that's more important, and that's going to create a framework of mind where you can explore more and enjoy that experience. So neural networks, as the lesson speaks, as we all know, this is usually presented when we talk about neural networks. There is an input layer, there is an output layer. You go with the real world scenario, and then you try to make sure you get it in a form which is understandable by the network, very popularly called as feature engineering, an upcoming field. And then you've got a lot of hidden layers come through node, and then you've got the output layers. So how can we understand this complicated process? This looks really complex, right? So what is happening in each node? Most of the videos, even if you look back, they explain it to a great deal, but a lot of papers make it quite difficult to approach it. My way of doing it is to really simplify it down to one or two nodes from right after the perceptron algorithm which you've seen, but a step less than, more than that, but a step less than the neural network which you build. So it's somewhere in the middle. Take a couple of nodes, one or two layers, and a simple output. Take one or two images, not more, and then run through that pass by printing out all the matrix values node by node. When we do that, we get to understand what's happening internally, and why exactly forward pass and backward pass are so important, why back propagation is seen as an important concept in neural networks, and without back propagation the entire process comes down to nothing. Well, it might seem a far-fetched idea, but what is in the real world which we do when we look at a lot of the products which we see in day-to-day world? Let us look at some of the examples, and being someone from automotive and aerospace engineering, I brought a couple of examples for you. As we go along the mentorship program, we'll look at a lot, but in this presentation it's primarily going to be automotive example, and maybe a bit I will touch on aerospace, but I got one more example from a completely different perspective, from fisherman's net. What has it got to do with automotive? What's the relation between automotive engineering and fisherman's net? Well, when we pick up examples from completely different scenarios, it opens up the way we think. When we look at that kind of scenarios and we go back to the industry, we will be in a position to apply our knowledge to different scenarios which we may not have seen before. So that's the reason I'm bringing you completely different set of examples and collating them together. A modern automotive, a modern car, if you look at it, you can see many parts: fenders, nose, mirrors, tailgates. An engineering student, or even an engineer, or even mechanics can go a step beyond and look at the body in white, look at all the internal components, engines and stuff, and it becomes really important. Why it becomes important is because of issues which we might encounter. What sort of issues? Well, imagine you're driving the car and you're faced with an emergency incident in a car. Fortunately, you're at a point where you can slow the car down on the highway and take it to a hard shoulder and just take it back to the workshop. Imagine a flight which encountered an emergency incident. Probably the pilot might land the flight safely, and then we got to analyze the situation, analyze the incident. When analyzing the incident, usually they start with the parts and the part diagram. Look at the car, it has got a lot of parts, a lot of assemblies and sub-assemblies within it. So they usually start with the assemblies and then drill down to the particular part where you got sub-assemblies and think about what might have been the problem in the sub-assembly, and then you look at the parts and then you analyze the parts. When we go through the details of it, we get to know what exactly went wrong, and what went wrong becomes really important to understand how we can fix it. A typical automobile car can have 1500 2000 parts, around 4000 to 5000 processes behind it. It's globally sourced as well. It's really complicated. Neural networks are no different. We got to go through the same process. For example, imagine a hydraulic circuit in a traditional car. And if there is a problem, we take that circuit out, we take it to the lab, as you can see it in the second slide. We pass a unit fluid through it, and then we check if it comes out through, if there are leakages or not. And then we look at every single pump, every single valve, see what happens, and we look at the return line filter, we look at the motor, and we look at the relief valve and how it functions, and make sure that circuit works. Neural networks are no different. This is going to be the fun part. This is the part where I ask you to print the matrices and print the numerical values and see how it works on a unit data. And that makes quite a lot of difference in understanding it. So unit testing becomes key in fixing and understanding issues. Well, we move on to another example, a fisherman's net. Well, here is a happy fisherman. It's a fantastic morning, and he's happily starting his work. So look at the fishing net. Let us analyze the process of the fisherman's fishing task. The net is all squashed up. He throws it. There is no form. It's hard to even model it as a surface in a computer design tool. But what exactly is a net? Well, if you look at the net, it has got a lot of knots. It's all tied up. It's almost like a neural network. It has got nodes. It has got the nodes which influence other nodes. It can be pulled and it can be squished. Well, the process continues after the fisherman throws the net. It falls on the water. It goes underneath, catches the fish, and then is ready to pull it back. Now look at the scenario. Well, can we see the change in the shape of the net? It has come to a form which can be modeled. It's a curvature. It's a surface. We can easily feel it. So a lot of differences between a forward pass and a backward pass. The forward pass is almost like the first photo which is all squished up. It's not usable at all. The backward pass is the part where you got all the fish, you got the weights in your notes, and there is a definite form. That makes a lot of difference between the forward pass and the backward pass. So that should help you to understand why the matrices which you are looking at are all over the place in the forward pass. While you compare and you use an optimizer and the gradient descent happens, there is a pattern, there is a form to the net, and then that form helps you to really go out and test and validate and prove that your neural network is a good model as well. So that should give you the overview on why we need the mathematical basis and the background from a different perspective. Now let us look at the mathematical intuition behind it, and I have selected really two narrowed down topics. No complicated mathematics, no long formulas. Gradient and Jacobian. Gradient, I wanted to talk about it because gradient descent is the backbone. We all know it. And Jacobian because maybe I like it. No, not really, because it's irrelevant. Well, we all know about derivatives. We have done calculus. Well, let me brush it up. Rate of change of a function. It's a measure of sensitivity to change is what we call as derivative. Change in y with respect to x. For example, distance with respect to time. Hunger with respect to time. I might be hungry in 10-15 minutes. Another way to look at it. We all hold a cup of tea probably when watching a presentation, or a cup of coffee. So it might get cold, and you might feel thirsty as well. So thirst with respect to time. The derivative is an example of that. So simple ways to look at it. Gradient is a multivariable generalization of the derivative. It's just generalized form. And gradient is a vector valued function as well. It's different from derivative because it's scalar valued. We know scalars and vectors. Let me briefly touch you on that as well. Well, the temperature of a plate or pressure on a cylinder, you look at it and say it's scalar because it's got magnitude and no direction. Vectors have got magnitude and direction. That makes a lot of difference. Gradient isn't in that in our lessons, as we have seen from the Mount Everest, which Lewis talks about. It's about coming down from a gradient, and coming down might mean in a real world it might mean 3 dimensions, but it could be much more dimensions. If you map time to it, it becomes fourth dimension, right? So there are more dimensions in real world problems, and knowing the direction always helps. Jacobian is one form of vector derivative with respect to another vector and helps us to arrive at the additional parameter which is going to help us to find the direction. And it always helps because the position information helps, as you can see in the third graph, while you're doing the gradient. Instead of achieving that local minima, local maxima, you move forward and you want to achieve that global minima condition there. So that's something which really helps, but a lot of scenarios even the local minima would be good. And that's the mathematical intuition which I wanted to build using this slide. So let us review all the things which we've seen today. Well, there are references to the lesson. It's to the lesson 4. We have got notes in the GitHub which you can refer to with all the transcripts, and we have got GitHub code as well. If you require further examples, feel free to ask us. Thank you for being part of today's session. Thank you for enrolling in Udacity's Nano Degree program, and hope this helped. And please come back to us if you have any queries, and good luck with your session and projects. Thank you. Bye bye.